So there's a lot of terminology. We're not going to really focus much on this one, but just to be aware, there's something called a multigraph, and it's a graph that allows loops. So a vertex with an edge that loops back to itself. So for example, if I had a vertex that had a loop back to itself, or I had parallel edges like this, then this is called parallel edge or parallel edges. I know they're not physically, mathematically parallel, but it means they just connect the two vertices in two different ways, and this right here is called a loop. We'll not really focus on multigraphs, but there are some applications of those as well. Now, also, it's important to know whether a graph is connected or not. So it's connected if basically we can somehow get from every vertex to every other vertex. So here's an example of a connected graph. The only way this will be a connected graph is if I could ultimately get from every vertex to every other vertex. Doesn't mean they have to be adjacent. It just means ultimately if I start at B, can I get to C? Well, sure, I can go to A and then to C. If I start at A, I can get to C, I can get to B. If I start at C, I can get to A, I can get to B. And that's called a connected. Now, all I would have to do to make this a disconnected graph is to remove one of the edges. So for example, if I had A and B still being connected, but C is over here all by its lonesome, then this is a not connected graph. And a graph being not connected will affect how we have to design algorithms. For example, if we want to find shortest paths between physical locations on a map, then if there isn't a route to get to another city, then we should have basically write that into our algorithm to say ignore any cities that are disconnected from the plan or the map. Here's also a really cool situation. This is an actual graph of the presumed terrorists are originally to have associations with 9/11. So you can see that there's a cluster of people, and this is just a small subset of that, but you can see that there are some hubs, and hubs are kind of like points that if you remove them, or vertices, if you remove them, the network would kind of fall apart. And you can kind of see that some of the hubs are the vertices that have the most edges connected. Like if you take off this red vertex, then that deletes a lot of edges. And so any vertex that, if you were to delete it, that takes away a lot of connections is often considered a hub. So Mohammed Abdi is clearly not a hub because by removing this individual, that network is still a strong network. But if you remove some of these inner points here, you can see that that could break up the communication between the left half and the right half of this particular organization. Okay, almost there. So now we get into some really cool stuff. An Euler path, so a path, remember, is just a path that starts and ends somewhere, is a path in which each edge of the graph is traversed once, perhaps different first and last vertices. So we'll take a look at a couple of examples of this. An Euler circuit is a path in which each edge of the graph is traversed once, but the first and last vertices are the same. So notice that it's still using the terminology path and circuit. A path just starts at a vertex and ends at some vertex. Whether it's the same one or not doesn't matter, but a circuit has to start and stop at the same vertex. But nowhere did we say that a path or circuit has to go across every edge or traverse every edge in the graph. But an Euler path and an Euler circuit are special types of paths and circuits where we do hit every single edge in the graph exactly once. So let me give you a quick example of that before we look at assess. So like a network like this, a really simple one, A, B, C, and D, if we connected them this way, then we could see that one Euler path, and here we'll also do, there we go. So we made this one a little bit interesting. Let's say I wanted to create an Euler path. So the only restriction is that I have to start at a vertex. I'm just going to pick A, and that I have to take paths all the way around and make sure I hit every edge. So one way to do that would be to go A to E, then E to C, then C to B, let's take that as the third edge, then B to A, that'll be the fourth edge. Then let's see. Let's say instead we did this. Let's say we took the third edge would be here. Then we'll do D to A. I think I'm going to end up building an Euler circuit here because I'm going to start and stop at the same vertex. But you can imagine that if we, as long as we travel along every edge exactly once, we could start and stop at a different point to create an Euler path. But here we're going to create an Euler circuit. So if we go 1, 2, 3, 4, 5, 6, 7, you see that we start and stop at A and we hit every edge exactly once, meaning not less than once, not more than once. And so our path in this case was A to E to C to D to A to B and then C and then A. Now there's no constraint on the circuit in terms of hitting the same vertex more than once. We can certainly hit the same vertex more than once, but notice that we did not double up on an edge at all. So this is an example of an Euler circuit. And this graph has an Euler circuit. And there's more than one. Of course, we could have gone the opposite way. We could have gone backwards, A, C, B, A, D, C, E, A. And you can find other ones where you go A to B to C to A to D to C to E back to A. And that would be an Euler circuit as well. So these are very useful. Suppose that a city is planning for its new trash program. The goal is for one driver in particular to leave the station, pick up trash along each city street, and do so at minimum cost. Can this be done for the network below, assuming the station is at vertex 1? So imagine that these are street networks, and what we want to do is collect trash along each street. We'll just assume that we're not going to worry about two ways or anything like that. We're just going to worry about making sure the truck goes along each of these edges. And so we want to avoid, one of the things we want to avoid is having to backtrack. We would rather somehow create a circuit, an Euler circuit in particular, to allow us to start at vertex 1 and end at vertex 1. So let's see if this is possible. So for instance, I can go ahead and go from 1 to 0, and then go from 0 to 18, and then 18 to 19, and then maybe I can go from 19 to 5, but wait a minute. Now I can't go back up to 0 because if I do, then I'm going to have to traverse one of the roads I've already traversed. So let me try to take a different path there. And I encourage you to pause and try to do this on your own as well. So here we go down to 5 and then maybe over to 19. But wait a minute. Now if I go up to 18 and back to 0, I'm going to have to go over one of the same edges more than once. So that's going to be kind of inefficient. Let's try a different path. Maybe instead of going that way, I'll just go downwards. And maybe we'll start here and go down there and go along here and along here and maybe here and then here and here. But wait a minute, I'm stuck again. And it seems to be that these top and bottom ones, these ones that have 3 edges coming off them are causing a problem. So if I start to think about this logically, I have to assess under what circumstances would this be possible. In other words, what must happen for there to be an Euler circuit? Which, by the way, this has no Euler circuit. So in order for something to have an Euler circuit, I need to be able to do 2 important things at each vertex. I need to be able to arrive at a vertex and to be able to leave the vertex an even number of times. In other words, here from 7 to 6, we arrived at 6, and then we left 6. But we have another edge coming into 6, and because we need to collect the garbage on that street, that means I'm going to have to come into 6. But if 6 was not my place of origin, then I would need to leave 6 again, and there's no other way to do that other than to traverse one of the edges that I've already traversed. And therefore, that leads us to the idea that there would be no Euler circuit. Now that holds true regardless of whether you start at such a vertex or not. So we could make the same reasoning above here. If I started at 0 and went to 18, that means I have to leave vertex 0. And then since there are 2 more edges, that means I have to somehow arrive, whether I arrive from this end here, but then I'm going to be forced to leave one more time. And if that was my starting vertex, there's no way to come back to it again. So we see that same issue whether it's the starting vertex or it's just a vertex somewhere in the sequence. We need to be able to arrive and leave an even number of times. So state this as a theorem. So basically, first of all, at every vertex, we need to be able to arrive and leave an even number of times. In order to avoid traversing the same edge twice. So stating this as a theorem, well, what does that mean? If I need to have an even number of arrivals and departures from a vertex, well, if I sum up the number of arrivals and departures, like here I arrived, that's 1. I left, that's 2. I arrived, that's 3. Well, that just happens to be the degree of the vertex, the sum of the number of times you arrive and leave. So we can state it like this. We can say that an Euler circuit exists only if, or if and only if and only if. So this goes both ways. Whether your Euler circuit is the condition and your conclusion is that all vertices have an even degree, or if you know that your graph has all vertices with an even degree, then you know an Euler circuit exists. So if and only if the degree of a vertex V is even, or I'll write it like this, V sub I, V with the subscript of I, is even for all I. That is, for all vertices. Nice. So as long as you count the degree of all vertices, and if you're using a computer and you're trying to find whether a graph has an Euler circuit or not, then an adjacency list is fantastic. Or using the adjacency matrix, you can just make sure that the diagonals for A squared are all even. Like this one, I can tell right away that this graph is not going to have an Euler circuit. There's no way I could start at n and get back to n by taking every edge once, because I'll have to leave n and then arrive back at n and leave n again, but then I can't get back a fourth time. So that's pretty cool. That's what we use Euler circuits for. There's an example where you want to build an efficient network. Now, just because it doesn't have an Euler circuit doesn't mean that all is lost. It just means that the route is going to have to come back along one of the streets. So it's not the end of the world, but looking for Euler circuits is nice because then that tells us that that's the most efficient route we can take. Okay, suppose the city needs to do maintenance on the streetlights in the above network. Does there exist a way to start at the station and to visit every intersection exactly once and back up at the station, thereby minimizing redundancy? So assume all intersections are equally spaced. Okay, so in this case, we want to do maintenance on the streetlights. And so if we start at, say, vertex 1, we want to hit every vertex exactly once. So I can go from, for example, 1 to 4, 4 to 7, 7 to 6, 6 to 20, 20 to 19, 19 to 18, 18 to 0. But I need to start and stop at the same vertex in order to minimize redundancy. I don't want to have to go along one of the same intersections. Like if I went this way, well, clearly At this point, now I'm going to have to visit a vertex I've already been at to get back to my starting point. So there is some redundancy. And the process of being able to start and stop at a vertex, visiting every vertex exactly once, is what's known as a Hamiltonian cycle. So it's a cycle that includes each vertex of the graph. In general, it is harder to determine one, and the theorem for existence of one is rather tedious. So we don't focus a whole lot on Hamiltonian cycles. Some graphs have them, so I could draw you a graph that does have a Hamiltonian cycle where, like right in the middle, let's say we have A, B, C, and D, like this, and we have maybe a connection there, and we have a connection here, and like this, and maybe we also have a connection there. So one possible Hamiltonian cycle would be to go from A to B, visit C, visit D, come back to A. We didn't hit every single edge, but that's not what a cycle requires. So this has a Hamiltonian cycle. Now there are some theorems that allow you to determine whether one exists. And here is one, and we're not really going to use it because it's really inefficient. Suppose G is the name of a graph with n vertices, where n is at least 2. If for each pair of non-adjacent vertices u and v, we can add together their degrees and it's at least the size of n, then G has a Hamiltonian cycle. So what we mean by this theorem is if we compare every vertex to every other vertex that is not directly connected to it, like this, in this graph. For instance, this does have a cycle because I can just go around this shape. But if I looked at this theorem, this would say that I have to sum the degrees of vertices that are non-adjacent. So for example, A and B are adjacent, A and D are adjacent, so I can only look at A and C. And the degree of A plus the degree of C, well, A has degree 2, C has degree 2, it's equal to 4, which is in fact greater than or equal to the number of vertices we have in this graph. We have 4 vertices in this graph, and so we've satisfied that condition. We would have to do the same thing for vertex B. B is only non-adjacent to D, and if we add together the degree of B plus the degree of D, we also get 4, which is in fact greater than or equal to the number of vertices in the graph. And the same thing would hold for vertex C, because C and A would be paired, B and D would be paired. So since the sum of these degrees is greater than or equal to the number of vertices in this graph, this definitely does have a Hamiltonian cycle. You can imagine that this can become very tedious if you have hundreds or thousands of vertices in your graph. Given you have to check every pair of non-adjacent vertices, this theorem may be harder to apply than to conduct a brute force search for a Hamiltonian cycle within a graph. So there are algorithms out there that will help us find these, and just because this theorem is not satisfied, even if it doesn't pass, doesn't mean that the graph doesn't have a Hamiltonian cycle. It just means that if this condition is satisfied, then it does have a Hamiltonian cycle. If this isn't satisfied, we just don't know. And we'll go ahead and stop there. So in the future video, we'll actually get into some features of graphs and how to perform some algorithms on those graphs. So see you then.